Hello, everyone, and welcome to today's public webinar with TPC entitled How to Read Your IEC Electrical Schematics, your International Electrical Schematics. My name is Ryan Smith, your host for today, and we are joined by our presenter and instructor with TPC, Marty Redman. He's going to walk us through some of the best practices of how to read some of these more international electrical schematics. You might recall one of our webinars previously really focused on the NEMA or North American standard for electrical schematics and a crash course on how to read them. You can go and feel free to check that one out. This one is going to be focused really on, by popular demand, the international electrical schematics, which kind of look and feel differently than the North American ones, and we're going to learn more about them. So before we get started with the official presentation, I would like to let everyone here know just a couple housekeeping items. First and foremost, this webinar is being recorded. And this recording will be posted on our website, the TPC training website, within about 2 to 3 business days after today's session. So be on the lookout for that, alongside all of our great webinar recordings that you can share with your coworkers and share widely and watch for yourself. The second thing is that the PDF of these slides as well is going to be available for you to download on our website at that time, which means you don't necessarily have to take screenshots of what you're seeing. You should be able to watch it and look at it back. And then the final thing is that this is an interactive session. This is live today. So what you are free to do and what we highly encourage you to do is to ask questions. And the best way to ask your question for Marty today is to use that Q&A button. So you should see along your toolbar at the bottom of this session a button that says Q&A. So when you type into that, you can type in your question that'll come directly to me and Marty, and we'll be able to get your question answered in the best way possible by the end of the session. So before we jump over to Marty and to learn all about some international electrical schematics, we would like to run a little poll today and just ask you a couple of questions from the audience, just to get an idea of who's here and a little bit of your thoughts and perspectives on international schematics. So I'm going to launch this poll right now, and you should see some questions popping up on your screen right about now. So we got 2 questions for you, and you can click using your mouse to answer each of these 2 questions, and then you can submit your response, and we'll be able to share these results with you. The first question we have is, how often would you say that you read non-US, in other words, non-NEMA, international electrical schematics on the job? Are you reading them often, maybe sometimes, rarely, or never? And then second, how comfortable are you in your ability to read a non-US, non-NEMA electrical schematic? Are you very comfortable? Are you kind of somewhat comfortable, maybe neither here nor there, you're neutral, or you're more uncomfortable in your ability to read these different looking schematics? So we're gonna give you just a couple more moments to register your answer. We see some really great responses coming in already. All right, looks like the answers are evening out a little bit, so I'm going to go ahead and end this poll. And then now what I'm going to do is share the results with everyone here. So what you should see is the distribution of who said what. So really, most people here are rarely or sometimes seeing schematics, right? So they might have a mix of the North American and the international schematics. So 37% of you said rarely and 35% of you said sometimes. That's great. So we basically are going to see these on the job sometimes. And the second thing, really more of you than not are pretty uncomfortable, somewhat uncomfortable. 40% of you are pretty uncomfortable in your abilities in reading schematics, which brings you to this webinar to get a little bit of info that might prepare you to take an official schematics reading course after this. So I'm going to go ahead and stop sharing. And that should disappear from your screen. And now what you should see now, full screen on your side, is our welcome slide here that says, welcome to our webinar on electrical schematics. And if that is what you are seeing, then we are good to go. And I'm going to hand it over to Marty. Thank you so much for being here, Marty.
You're welcome, Ryan. Welcome aboard, everybody. We're going to spend some time today learning information about IEC equipment and their drawings. And so A little confusing to some folks, but we'll try to make it seem a little simpler. And that way, mostly industrial folks get these, but I know in commercial, sometimes there's machines that have these. So we'll kind of walk through some of these and make it so that you can understand them, because they are somewhat similar to NEMA drawings. They just look a little different. So we'll get there through our presentation today. I'd like to introduce myself to you. I've been in the electrical field for 50 years, and I started out in construction, little commercial, went into industrial for a while, and took my GI Bill and did a little more learning and got some new skill sets, and spent about 30 years helping design and building panel board plants, that make OSB, particle board, and those kind of boards. And I spent the last 16 years working for TPC, helping others to learn valuable information, practical information that we try to bring down to the students so that you can take that information, go home and use it. Or go to work, use it, I guess I should say. And so that's what we're going to try to do today, is make it easier for you to understand more basic things, because a lot of times we don't get any training on reading schematics. We're just supposed to figure them out. And I think they're like a lot of things. Once you get the key, it opens up in your mind and makes it a little simpler. Much easier to read. And once you understand how to do that, it can make troubleshooting much easier. And of course, if you don't have any prints, like I'm sure a lot of you guys don't, if you take one of our classes, we'll teach you how to draw prints when you don't have them. It can be done, just takes a little while. So we're going to learn a lot about IEC things. I think an important thing is that a lot of equipment has IEC equipment in it, but is not necessarily wired overseas. It might be wired in the United States. If that's the case, and it's really important to know, is that overseas, they follow a different process of wiring a machine than we typically do here in the United States. And so it may not be wired the way an IEC drawing is, because it was wired in the United States. So it's pretty important to know where it came from. And that information is usually on the print, if you have one, in the right corner, in the legend down below, the bottom of the page of it anyhow, to give you some information. So those are good places to check right up front to kind of give you a better idea of what's going on with this machine, because it's difficult with so many different machines coming from different countries, and not all these countries follow the same standards. So sometimes you just have to kind of work through things. And if you kind of understand NEMA and you understand IEC, you can probably make pretty much whatever print you see, make it something that you can understand and follow a process with it. So between the two, that really helps. So with that being said, let's kind of move forward. We're going to talk about understanding how electricity works, because if you don't, then the print's not going to help you a lot. So we're going to talk about that and all the different types of drawings. There's lots of different drawings that come with machines, and several different types, and it helps to know where they are, because some show you where things are and some show you logic, some show you connection points. So those are all important things to know. Knowing your symbols and abbreviations. Well, guess what? If you get to know NEMA and you get to know IEC, that will help you out a lot. If you don't troubleshoot often and you don't use them very often, it's kind of hard to remember all these things. So, we got that good thing called the internet now, and you can go out and find a lot of information on both. And there's a lot of symbols. And I think as you download them or print them out, you're going to find that They're not always exactly the same. Depends on who made them and who printed them out. So we'd like to think we have standards, but not everybody follows them. I would tell you that if you get CAD drawings, which most people do now, you're probably better off. You're going to be better off, and they're going to be more the same if they come from a CAD bank of symbols. So that helps us a little bit. Understanding how devices operate in a circuit. There's lots of different devices, whether you have hardwired timers and relays, motor starters, contactors, all those things. It's very important to understand how they function and why they do what they do. So I always tell people that this is a good time to spend on your breaks or lunch, or when you're not busy fixing something in a maintenance shop or someplace where you have this equipment, is to, learn about them, take them apart, see what makes them work, how they work, what makes them go bad. There's a couple of things about just about any electrical devices that you should always know, and imprinted on them someplace is the voltage and the current that device can operate under. And a lot of times people put in devices that can't handle the current or the voltage, and that's why they're failing. So back to understanding more about how things work so that you can get to the root cause of the problem. That's what you want to do. I don't think you want to be fixing it every week. I think you want to fix it and go away and kind of forget about it for a while. So root cause is a good place to get to and fix it so the problem goes away. One of the other things we're going to talk about is title blocks. Most drawings have them, and they're going to give us some information in there. So we're going to talk more about those, but they give us a lot of good information. Here it talks about checking for keynotes and updates to the drawings. Typically, when we get a drawing, there's changes made to it. And when they update it, we should always check for those updates and drawings, because they can save you a lot of time and or money sometimes. So pretty important to check those. And understanding the difference between NEMA and IEC drawings. As we walk through them today, you're going to see that the symbols are different, but somewhat similar to each other. They operate pretty much in the same way, but have different termination numbers. And so everything's just a little bit different than we're used to seeing with North American drawings. And so sometimes hard for us to figure out, but we always got to follow that flow back to understanding how electricity works. We need to understand the flow and how the circuit operates, and that'll give us a much better understanding if we have that. So we're going to walk through some of this stuff. And so understanding, how electricity works is that source of energy. The print's going to tell us where that source comes. And with most machines, there's going to be several sources of energy. Typically, you have a higher voltage one, which most of us probably would say was 480 in some cases, might be 240 or 208, but somewhere in there. And that's usually for our motor loads and those kind of things. And then we have transformers also in that panel sometimes, and that's usually for our control voltage. Could be DC or could be AC. That's going to be on the print. And those are very important things to know, because if we're troubleshooting and I'm using an electrical meter, number one, I need to know to get it on the right setting. And number two, if I'm checking something, I really need to know what the voltage is supposed to be, not just accept something that my meter tells me. So I should know that, I'm working on 24 volt controls, or I'm working on 120 volt controls, and all that information is going to be on that drawing. So our source of energy is important to know. Also, we're going to get our overcurrent protection devices on our drawing. So fuses, breakers are important to know. It's important to know where they are So if I need to get to them to replace the lockout, whatever that is for any safety issue, I know where it is. And so a control drawing is not going to tell me where that is typically, but there'll be another drawing that tells me where the power is. So before you work on any machine, that's kind of something you should already know. That's something you should have checked first. Where's the source of power coming? Where is, when I open up a disconnect, I know that there are no other voltages in that panel. And so for some machines, that may be several disconnects. It's hard to say. It just depends on what you're working on. So our source of energy is important to know. Our load, what's our load? Well, you know, we could be feeding a panel. We could be feeding just a motor starter and a motor. I don't know, but that's on our print. And so we need to know what that load is, what the current draw is that's going to be on the piece of equipment, whatever that is. So that's part of our circuit, right? We got the source, we got a load. Then we need to know, you know, the current flow. What should it be? When it comes to motors, I would tell you that it's always very nice to know what's the running amps. What's the running amps on that motor? So when that machine is out there doing its work at 100% of whatever it is it's supposed to be doing, I've checked that motor and I've written down what those running amps are. Those are very important to me when I'm troubleshooting or even just doing maintenance, is to know what that should be. So when I check it, and I've got a motor that's good for, I don't know, let's say 15 amps and it draws 12.5 when it's doing its thing. And I go there one day and I check the amperage on it and all of a sudden it's up to 14.5. I shouldn't say, okay, because it's not 15. I should say, how come? What changed? Why am I doing more work? Those are things that help. I could have a bearing going bad. I could have a belt dragging. I could have a screw dragging on the bottom of the trough. I could have all kinds of different things, but when I'm drawing more current, that means that motor is doing more work. I need to know why. Okay. Then to complete that path. So that happens on the conductors or wires, as we call them, that we connect the device from wherever the source is back to the source. So if we have three-phase power, we have 3 paths for current to flow. If it's single phase, we have 1 path for current to flow. And so we need to know whether we're working on 3-phase or single phase. And so we need to know that if I don't complete a path, the load is not going to come on and do what it's supposed to do. I always have to complete that path. So we talked about different types of drawings. Single line diagrams usually show our distribution, and we call them single line because we know that there's 3 phases, but instead of having to draw a whole bunch of lines on a paper and confuse people, we do what we call a single line drawing, and everybody knows that there are 3 phases that we're working with. And so typically a 1-line diagram does not show us where anything is. It just shows us the power coming in, disconnects, motor starters, MCCs, all that thing, however that power is distributed throughout the facility or building, that's what a single line is going to show us. So it can help us see how things are, but not where they are. Wiring diagrams give us locations of terminations and where things are on a particular, in a panel, on a machine, those kind of things. Some people may not have wiring diagrams. They may just have schematics. So it's really hard to say. A lot of times those wiring diagrams just get lost. I don't know, sometimes they end up in somebody's locker or something, I guess, but we don't have them. So wiring diagrams can help us know where things are. Schematic drawings, back to that information on the controls and relays and all the things that are in the box can really show us what set of contacts it goes through and those kind of things. And then we have ladder diagrams, or for our control circuits. And we use ladder diagrams because it shows us the logic for the path of whatever it is we're trying to turn on. It doesn't show us where anything is, but it does show us the path. Quite often it shows us termination points. And so it makes it easy to use to troubleshoot the circuit, because a lot of times we don't really care where it's at. We just want it to work. And so it makes it easier. I just tells me where to go and shows me where things are on there, how the logic should be and what's in that line of logic, whether it's push buttons, limit switches, motor starters, solenoids, whatever it is, it's just there in a real simple form. Then we have floor plans that will show us where some of the lighting panels and distribution panels and stuff like that are sitting and where they are in the facility, which can help if you have a large facility. Then we have site plans. You may have a facility that sits on, I don't know, 15, 20 acres. It's hard to say. It's kind of nice to know where the manholes are, where the transformers are, where the wires are routed and those kind of things. So it kind of gives us an oversight of the facility and shows us where all those things, those sources of energy and whatnot are coming in, and gives us a place to go. Typically, they have numbering schemes on them. You just have to look at the print to get a better understanding of what those numbering schemes are. Okay. So what I would tell you is that all of these different types of drawings are drawings that we go over in our schematics classes. We always welcome people to bring schematic drawings and stuff to our classes so we can help you talk about them and get a better understanding of them. So if you have some issues, you need to know a little bit more, please let us know, get a hold of our salespeople, and we'll try to work that out for you. So talks about knowing symbols and abbreviations. Well, again, depending on whether they're NEMA, I, or C, come from China all over, they can be different all over the place, but you need to know that you have all these different principles that you may need to know, because sometimes the mechanical and electrical and in the building and whatnot all have to tie together somehow. Learning all of these symbols and abbreviations is very difficult if you don't work with them very often. But what I would tell you is that most prints come with a legend page, and on that legend page, it explains what all the symbols are and abbreviations are. So if you have that page, you got to step in the right direction. If you got a print that doesn't have that, it makes it a little more difficult. Here it says you must know what the symbols mean or you can't troubleshoot. And so what we're talking about, is normally open, normally closed contacts. And there's so many different type contacts and relays and all those things that it's pretty important to know your symbols. So when you're going out on a machine, maybe you need to take them with you if you don't have all that information on your drawing. But if you think about most drawings, there's not a lot of words on them. They're just got lines and these symbols, and we have to know what they are so that we can follow this path to get our device working. So on most drawings, there's power and controls. So back we talked about power, that 480 volts or whatever, and controls being 120 or 24 volts AC or DC. We may, depending on your machine, you may have a couple of drawings, one drawing just for power and another set of drawings just for controls. It just kind of depends on how large the piece of equipment is or the process is. So got to know both because when we're troubleshooting, when something doesn't run, one of the things we're trying to figure out, is it a power problem or is it a control problem? And so we're going to have to troubleshoot both of those skill sets to find that out. Okay. And that's why on the prints and things, when I know what the power is, when I say, it's power, is that 208? Is that 240? Is that 480? Could even be higher, 4160. It just depends. So that's what those prints help me with and give me a better understanding where I'm going. And also the equipment and safety procedures I need to use and equipment I need to use when working on that power. So those are all important. So let's talk about some power symbols that we're going to see on drawings. And these are all IEC drawings. Is a three-phase fuse disconnect switch. Now, I've seen several different drawings of this particular switch, and some show the fuses on the angled lines and some show them below. So it really depends on the manufacturer of your equipment. But one of the important things is that you see our numbers on our print there. And so this is a typical thing with IEC, and that is 1, 3, 5 are on the line side, 2, 4, and 6 are the load. So as we go through our prints today and start talking about them, one of the things you're going to see is odd numbers are source, even numbers are load. Now, there again, I'm going to tell you that this is if this machine came from Europe, Germany, Switzerland, someplace like that. If it came from the United States and it's got European equipment, I can't tell you that it's wired that way. Okay. We're also showing you some auxiliary contacts. Almost all disconnects now have auxiliary contacts in them because we're sending information about the whether that disconnect is open or closed, probably to a PLC, to a building automation system, so that if the machine isn't working, somebody says, well, you didn't close the disconnect. And that's what we're getting. We're getting an input to some device or someplace so that we know whether it's opened or closed. Now, I did not put a symbol up here for a circuit breaker, but if it would, we would have these same contacts on it. And if it tripped, it would trip and let us know that the reason that the equipment is not running is because the breaker has tripped and it is now open. So it helps us troubleshoot because we're not talking about having to go find out. In most cases now, we got a screen someplace that's giving us that information right up front. Telling you right away, hey guys, you were doing maintenance and you just forgot to close the disconnect. Go back, close it. These contacts typically interlock controls and will not let that starter come in unless that disconnect is closed. So we got some information, some interlocks and stuff going on here, which is makes things much safer. This is a non-fused disconnect. So there again, we've got our odd numbers at the top, even numbers at the bottom with some auxiliary contacts. Now, do all disconnects come with auxiliary contacts? And the answer to that is no. It depends on what we're using it for and if we need that information. So almost all of them now has a kit that you can buy that can just screw right into that disconnect and give us a normally open, normally closed set of contacts so we can get some information from it. So if you need that information into some kind of building automation system or PLC or whatever, you can get that in there. This is just a contactor, okay? So a lot of you might have lighting contactors in a building. So this is a symbol for it. And again, our 135, 246, same thing. So, and just remember that, on this particular, it's just a symbol. In a print, you'll probably get ratings and things in it, but not just on this symbol. And this is a overload symbol for three-phase system. And typically, as we go through some prints, I'll show you that we probably think of our overloads always being attached on the bottom side of a contactor, which we call a motor starter. But Europeans don't do that a lot. They have a little different scheme to their systems. So we'll talk about them later, but just remember that, we've got this This 135-246 is always on all their equipment. That's their pass. Okay, so remember, we're always trying to complete pass. Now we're going to talk about some control devices, not all of them, of course, because we don't have time to talk to all of them, but maybe some of the ones that we see on a more regular basis. This here is just a normally open contact, but because it has this little symbol right here and a dotted line, tells us that somebody's going to do something to this contact. This is just not a contact on a motor starter or on a relay or something. This is special. Okay. So one thing we know right away is that it's normally open. We're going to talk about what these numbers mean in a little bit, because they're also telling us that this is a normally open, because anything that has a 3 and a 4 means it's normally open. So we got this normally open push button and it's momentary. So when I put this little block over here with a 1 in it, it tells me immediately that I know that this is a push button. Could be a start button, which is kind of typical for if it's on a motor or something. But with this here, and this symbol knows that I'm going to push that, and it's momentary, and it's probably going to do something. I'm going to jog something. I'm going to start a motor or whatever. But when I look at that symbol, I know. Okay. So here we have a normally closed symbol. And I've got the same symbol here, which is telling me somebody's going to push it. So that's going to tell us that it's a normally closed push button, momentarily closed push button. So kind of back to our stop start stations that we have on a lot of our equipment and machines. And when I get this little box with this 0 in there, I know that this is a stop button. So I know that right up. So I get this symbol on a print, and I know that it's a stop button, and it's normally closed. And this number tells me it's normally closed. The second digit here, this 1 and 2, means it's a normally closed contact. And here is just a contact. So, or excuse me, this is a limit switch. And I know it's a limit switch because of this little wedge that's on here. I know that something's going to push it closed. So I know it's normally open. And there's that 3 and 4. Remember we talked about 3 and 4 over here being open? Well, 3 and 4 mean this is normally open. Okay, normally open. So I know it's a normally open limit switch. And I know something's going to push it closed. So I need to know about limit switches and the type I'm using and all the things that I can do with them, because there's a lot of things that are in a limit switch that some of you may not have had experience with yet. Here's a normally closed contact. So back to our 1 and 2, we keep talking about this 1 and 2. And this is a pressure switch. It's got a P. So you're going to see a lot of contacts that are similar, but they put a different letter in here indicating the different type of devices. This is a pilot light for IEC. In some places, you might see a letter by it or in it. Most of the time it's like this, and next to it, there's the words red, yellow, or whatever. But typically, that's all you're going to see on a pilot light. This is a coil. So most of their coils have an A1 and an A2 on it. Most of the time, not all the time. So we didn't draw it that way, but it's a coil. It could be a relay or a contactor. I'm going to show you how to tell the difference in a little bit. This is a solenoid. It could be air, could be hydraulics, water, but it will say next to it what it is. But this also typically has an A1 and an A2. A2 is always down here. A1, remember we talked about source coming in here. And so the source comes in, and then the other side is load or back to neutral or back to our source of power. Here's a normally open contact. So we have a normally open contact, and obviously we have those on auxiliary contacts. We have whole relays full of these, and we will talk about that, but you can see it's a 3 and a 4, which means it's open. And here we have a normally closed set of contacts. And back to our 1 and 2, back to our 1 and 2, okay? So there's a lot more symbols to go over, but these are some of the basic ones you're going to see on most prints. And remember, it says here, drawings are drawn in the de-energized mode. So when we talk about these normally open and normally closed, that's as if that piece of equipment, that device is sitting on a shelf, hooked up to nothing. That's how it's drawn in a print. So you got to remember that when you're looking at a print or you're on a machine or something, there could be something that's not in its normal position when everything in that machine is de-energized. So they're just showing you how it's drawn. So there could be a cylinder pushing it or a pressure switch pushing it. Hard to say what it is, but that's again knowing your machine. This is kind of a typical IEC limit switch. And here we have the inside of the switch and our contacts. So we got the normally closed contacts. We got the normally open contacts. That's normal. Now, if you work with a lot of hardwired stuff, one thing I would tell you that in some of the better limit switches, more expensive ones, up here in the operator section, there's actually cams in there, and you can make the switch so that it only works in one direction. So if I push it this way, it works, but if I push it this way, it doesn't. And I can set it up for vice versa, or I can make it work in either direction at the same, either way it goes. It can give me pass current through it. So if you have problems or you're checking switches or replacing, make sure it doesn't have that up there, because it may only want to be operating in one direction, and the other direction could cause you problems. Now, the other problem that we have sometimes in prints, which people don't notice, is when switches are drawn in the held position. In other words, when the machine is de-energized, there's something sitting on that limit switch already. So what we've got is a normally closed switch held open. And you have to understand this, because you could wire a switch. If you don't catch that, you could wire it wrong and cause yourself a lot of damage. So you've got that normally closed switch held open. And of course, then we have a normally open switch held closed. That means something's on it, pushing it closed. And so when you're in a hurry troubleshooting, make sure you pay lots of attention to this. This is your typical NEMA drawing. And so hopefully you're used to one of these, but I only brought this in here because it may be a little easier to show you the paths that current take. We have all these paths that current can go through. And if we complete that path, you know, the device will work. So as you look at this, if we have power up here and our circuit breaker is closed, we should have a green light on, because that's a completed path. We got a normally closed contact going right around to that, okay? So these are probably symbols of what you're maybe more used to seeing than IEC, but we're gonna show you that these basically work. IEC works basically the same, just looks different. This looks different. So going from this stop-start station with a couple of pilot lights, holding circuit, we're going to an IEC drawing that has the exact same thing. Okay, exact same thing. Now, drawn different and somewhat confusing at times. But these numbers here are like our rung numbers or spaces, whatever you call it. So If you ever look at their drawings all the way across the top, they have these spaces. And so we have to adhere to those spaces. We need to know if those spaces mean something, okay? So there's our spaces in there. And so here we have a stop-start station, basically what we have. But with IEC, and again, if it comes from Europe, you have the very first contact. If it's a motor, it's going to have an overload in it. So this is a motor starter. We're going to start a motor, and this is the overload. There's our little diagram, right? So it shows our little overload, and that's going to be the first thing in the rung. That is not the case in the United States. We do not do that. The National Electrical Code says we can't, but in Europe, it's not the case. So in an IEC drawing, when you see this, this is the overload, okay? And you know, just like ours, they have manual ones, they have automatic resets, they have electronic ones, whatever they are, but it's an overload and has special numbers. Then we come down to that normally closed stop button. There's our 0, there's our 1 and 2. 1 and 2 means it's normally closed. And typically we would show a start button here, but they show the start button over here. So there's that 1 and that symbol again with 3 and 4. And the reason they show it over here is because the normal path of current is going to be through this contact, which is the holding contact. Now, what they've done here is they've given us a number, this number out here. All their numbering systems try to take you someplace. And this is an A7.02K11. That's what this guy is. So what I know is that the contact changes whenever this thing is energized. Whenever this coil is energized, this contact's going to change. And typically below here, they're going to show us what contacts are being used. So one of the things that happened, we talked about, is how do I know whether that's a relay or whether that's a contactor? Well, this one is a relay with auxiliaries on it. And I know that because all these contacts that are showing here are double-digit numbers. So remember, 3 and 4 tell me it's open, but the 1 in front of them are telling me it's the first contact on that relay. So I have all of these. This is what's on my auxiliary contacts. These numbers over here are telling me on what space or rung it is. So this one's used in rung 1. Here's rung 1. And here it is. This one's used on rung 3, normally closed. And if I go over here to rung 3, there it is. But down here, connected to that, I've got some power contacts, and power contacts are always single-digit numbers. So on a different drawing, on B1, because you see this is A7, in a different group, B1 is where this set of contacts are being used. So I got to go to group B and find this, but it's telling me that this is a contactor with auxiliaries. This is telling me that I got a red light and I got a green light. Lots of information and rungs. So we're trying to connect everything together. So here's how we're connecting it together. We had that number A7-02K11. So Europeans are pretty good with print groups. So this is print group A7. So I could have A6 and A5, but this is A7. So that's where my number comes from, A7. It's going to be down here on my legend. Here's A7-01 and A7-3, and with some arrows. So this is saying the drawing before this was page 1. The drawing after this is page 3, and the drawing I'm on is page 2. Okay. So here's my print page 2. So I said what group I'm in, now on what page I'm in, and this is the device type. So a K is used for a relay or a contactor. You already went through how I can determine which one is which, so I got a K. Then this is my rung number or space number. It's in 1. So here's my space. Here's 1. Okay. So I'm in rung 1. And this is the number of loads in that space. So some some rungs or spaces have enough room that I might have 2 or 3 different loads in the same rung. So this is saying it's just got 1, and there it is. Here's my load again. So it's giving me information. Typically, their numbering systems are all trying to take you back where things are so that you can find them. Okay. Not all prints are numbered really great, but most of them have something that you should be able to work through. Here's all those contacts we talked about. So in my relay here, again, I've got my numbers, tells me what they are and what rungs they're on. And if this was to a different page, it would have that information out here. I have one I can show you in a little bit. This is kind of power and controls all together, but I want to just make sure that you understand no matter what it is, odd numbers are the source, even numbers are the loads. And I'm going to tell you, Europeans will run a wire 3 foot longer than it has to be to make sure that it gets connected to the right place. And they do that so that they know where the power is going. That's why they have all their numbers on their devices, so that it makes it really easy to know where things are coming and going to. And like I said before, typically coils, whether it's a relay coil, a solenoid coil, anything that's a coil typically has A1 and A2 on it. Okay, so here's a contactor, and this one, Siemens has put both sets of numbers. So I have 1 and L1, 3 and L2, and 5 and L3. So we talked about the odds being up here and the load being down here. Now I have places for auxiliaries that can fit on here, can snap right in, and that way I can have power contacts and auxiliary contacts on the same device. And this is one I told a member, said if there's a number over here, it'll tell you. So this set of contacts right here, this 31 and 32, are being used in group A7 on page 3 on rung 7. So it takes me right to it. Makes it easy to go there. One of the big difference with European equipment with motors is they typically use these manual motor protectors, or a lot of people call them manual starters or whatever. But this is why you don't see overloads on the bottom side of the contactors for their motors, is because the overloads are right in here. So this is an auxiliary contact, which can go right on the side. I have a button here that lets me operate these manually if I want to check them with my meter. I have a dial here where I can change the current draw for this particular protector. Like a lot of overloads now, you have ones that you can set higher or lower depending on what it is. So there's a current group there depending on what it is. And this one has another place for auxiliaries in here. So we got lots of places for auxiliaries in here. And this will also can be my lockout tag out. So a lot of these, I just pull this little gray tab out and my lock will go right through this hole. And they've also made it now so that we can comply with 70E. We can have through the door switches that hook right on here. And now instead of opening a door to turn off a motor protector, I can do it from outside the cabinet without ever opening it up. Great for guys that are doing maintenance, or for the operator, maybe it needs to turn it and lock it out so he can change a saw blade, let's say, whatever that might be. And so our numbers are the same here, back to 1, 3, and 5, same way down here. So the scheme is the same for all their stuff. Now here's what we're talking about on these relays and contactors. So on a relay, this is really important here to know what things do. And we've talked about this. 3 and 4 are normally open. 1 and 2 are normally closed. Then time relays overloads get different numbers, and other devices, special devices have different numbers. But so it's very important to know these. So here we're looking at this 1 and this 1. It's the first set of contacts on my relay. First set. The second number is going to tell me whether it's normally open or normally closed. This relay is kind of doing it all for me. It's telling me what the number is, and it's also putting an NO up there or NC. But if you just have a number, that's all you need to know. So if you got this little thing here and you can keep this in your brain, they're all the same. Those numbers are telling you which set of contacts it is. Could be the second set of contacts, but it's telling you which set it is. So back to some of our IEC symbols. We've got our limit switches, normally open, normally closed. Again, our numbers are the same. A foot switch. You guys can get these off the internet, but just remember these numbers, guys. Remember these numbers. So the source is going to come to 1, and this is going to go towards the load. It might go to another switch or button or whatever, but you always know where the source is with European drawings. So we got our relay contacts here, pressure switches. Of course, we got our mushroom head buttons and momentary buttons. Our overload contact, we looked at that in that one print, okay? Contactor coil, pilot lights. So here's kind of a good IEC drawing to talk about. Back up to our rungs or spaces up here. So we got to follow, we got to keep kind of have an imaginary line going up and down through here, okay? And so this drawing's got a little bit of everything on it. It's got some hardwired stuff, and it's also got some PLC outputs up here. That's what these are. That's our symbol for 1, another output. And we have 2 loads. So if you look at this, this output is turning on a relay. And you notice this one's, the number on this one is B601K41. And if you look at the load down here, it's B601K42. This is the second load in the rung. So that, again, that's what it's showing you. And what we know down here is by looking down here is that this is a contactor with auxiliaries. Why? Because these are all single-digit contact numbers, and these are all double-digit numbers. So we know we're doing both on this. When it functions, it's going to close some main contactors to, in this case, turn this motor on. And it's also going to have some interlocks, because what we're looking at here is a forward and reversing contactor. And so we're going to have contacts that interlock it. And remember, we said that these numbers here tell us what space it's in. Well, this says that all of these are in space 2. Well, guess what? Right here they are. Okay, so we got this 4-2. This is 4-2. So there's those contacts right there. Okay, we know where they come from. And if we go over here in space 5, that's my reversing set of contacts, right? There's that B52. Well, guess what? In rung 5, we also have 2 loads. Okay, so it's important to piece together. And down here, we got that number that says that I got a set on a different, on A7 on a different page. So I've got something else interlocked with it. And so it's important to follow these numbers. These numbers will take you places. And if you notice, every one of these sets of contacts tell us if it's a relay contact right away, because 2 digits right there. This is the second set on this relay. Where this is coming from, okay? In this case, we know where it's coming from, but it's the second set. All of these, this is the third set. That's the first set on the relay. Again, first set, second set, third set, it gives us all this information. In here, it's even telling us that we've got power from right here going to a different drawing and a different group. It's a B group, page 6. Okay, so we're going to B6 in this case. So all this information, remember we said comes from the legend page down here. Tells us which way we're going. Even our three-phase power is up here. And it tells us where it came from and where it's going. Where it's going. Now, one of the things I want to show you, because it looks like we're about out of time, Ryan, I think, is one other picture here. And this is pretty typical with IEC installations, in that this is an input. And look at all the contacts that have to be made to get an input. This is something that we don't do, and typically in the United States and North America, is that we give every one of these contacts an input. Because right now, if something doesn't come on, or I don't get an input, however you want to look at this, I don't know which set of contacts is bad. I'm going to have to troubleshoot all of those, or I can start in the middle and go both ways. But something we do different in the United States, this would be an input, this would be an input, this would be an input, and this would be an input. And now I can look at a PLC and know which one of these is bad, which one didn't make. And then I can go to wherever it is, because it's giving me the group number, it's giving me the page number and the relay or contact number, and I can check them out and see if they're making or breaking. So kind of important to kind of get this to all flow together. This has been kind of a crash course, guys, as to how this works. And so we can definitely help you and learn a lot more about this. You there, Ryan?
Yes, I sure am, Marty. Thank you so much for the great presentation. We have a couple questions coming in. We have a couple minutes to answer questions. So we're looking at the Q&A line right now. Got a question for you, Marty, about maybe some real world examples of the usage of the first and second symbols you showed on the slide back when on the push buttons, the normally closed and normally open push buttons, the momentary push buttons. Can we get a quick real world example of what that might look like in the field?
Sure. That's just the stop start station for a motor, where you have the two buttons, the green button and the red button. The normally open would be the green button, and the normally closed would be the red button. And
Gotcha. Right.
The motor starts up or something comes on. I don't know that it's necessarily a motor, but typically we think of red and green buttons that way.
Definitely. Let's see. We also got a question about the NEMA drawing. Does TPC offer a NEMA drawing course? Absolutely. So our schematics reading 2-day course is really what this webinar should lead you into if you want to continue learning more. We talk about NEMA and IEC electrical drawings in that course, and we really go through a bunch of large schematics and learning how they work and doing some exercises around them. So definitely do check that out on our website. Feel free to call us and email us at this number if you want to see more information or you're not sure where to find it, but definitely tpctraining.com is a great place to start. Siemens, if they're made in the USA, do they use different conventions made than the Siemens Siemens equipment made in EU? Do they use different schematics, Marty? What would you say to that?
No, because all the Siemens equipment comes with European notations or symbols on them. That's just the way they are. Doesn't matter whether they're made in the United States or not. They all come that way. If you buy Allen Bradley, it doesn't, but if I buy the other, Allen Bradley basically has European style motor starters, relays, push buttons. And if you buy the European style, they will come with European numbering scheme.
Gotcha. I think the last question I can get to here before we close it is, what does PLC stand for, and how does it fit into a schematic?
What was the abbreviation?
Yes, PLC.
Oh, programmable logic controller, a computer that runs a machine. we have a PLC class. Actually, I think we have 3 of them. So if you want to learn more about those, we have a real basic class, but most machinery now has a computer that runs it. And we call the ones in most machinery PLCs because they're programmed differently than you would say your laptop computer that you're using right now.
Gotcha. And for Saul, who just asked a question about which course it is, I just sent the link to our answered questions. It's our electrical ladder drawings, schematics, and diagrams course. We're offering it almost weekly virtually online if you want to log in from wherever you are, or come to a location near you. Got some options there as well. So thank you so much. I know there's only so much we can get into schematics. Obviously, reading schematics is a career-long, years and decades-long endeavor for many people that you should just continue to learn. Just like we're showing here, remember, you should never stop learning. Try to find the nearest schematics to you. Try to learn the ins and outs of where the lines are going, what the symbols mean, and definitely consider some official training on the matter. This is obviously just an informational course that can't really get you a certificate or CEU or anything, but definitely with just a couple clicks you can and continue to learn. So feel free, if you're curious about your schematics you have, feel free to call us. If you're not sure what they're trying to say, feel free to call us and we can get you set up with the right information. So thank you all so much for being here and have a wonderful day.
Thanks, everybody.